Hello everyone, my name is Mohammad Taher. Today I will present um, high-electron-mobility transistor-based hydrogen sensor using I2 as a sensing layer. This work is a part of this project governed by the Lorraine University of Excellence with the collaboration of GeoRessources, Institute of Lafayette, 45 Energy, and Solexperts. At the very beginning of my presentation, I'll briefly describe the motivation and objectives of the work. Then I will show some potential areas where we can implement our proposed technology. And afterward, I will show why we choose this technology. In the second part, I will show how we fabricated our device in clean room facilities at Institute Lafayette. Then I will move to the characterization part of the device. At the very end, I put the summary of my work and future plan. So there is a number of technologies to measure the gas, like Raman microscopy, mass spectroscopy, non-dispersive infrared spectroscopy, and gas chromatography, and so on. And those devices are capable to detect gas concentration precisely and selectively. But when we think about the in situ online detection of the gas for years surrounded by the harsh environment and most importantly, size and cost, those traditional technologies come up with some drawbacks. That's why we propose a new semiconductor gas sensor technology called aluminum gallium nitride by gallium nitride based HIMT. Here you can see this is a 5 centimeter by 5 centimeter wafer, which is consists of more than 3,000 sensors. So the sensors are really compact micrometer in size. If we go for the mass production, the cost will be so low. The developed sensor can do in situ measurement of gases for years. Now, how we will detect different gases with this technology? You can see this is our function layer known as the gate of the transistors. By changing the function layer of the device, we can use our sensor for many different other applications like air quality monitor, healthcare system, in harsh environment, water quality monitor, and so on. Now, the question could arise why we choose this specific GaN material and HEMT structure. HEMT device is formed with aluminum gallium nitride and gallium nitride epitaxial group. This combination of high band gap and low band gap material create charges in the channel of the device. When we apply voltage between the source and the drain, we get the movement of this charge in the form of output current that we could measure. This device is a surface activated device. Any change in the surface state can modulate the charge in the channel with a high gain compared to the other conventional semiconductor gas sensor. So the device can detect gas with high selectivity and precision. This is how our device works. Thanks to the properties of gallium nitride, because of the high band gap, it provides high chemical resistance and thermal stability. We start now how we fabricate our devices. We start with the designing of the mask to print the image of the device on the wafer. Then we collect aluminum gallium nitride by gallium nitride wafer from our growth team. Once we have the wafer, we isolate each and every device from each other. Like now, we will consider only single device. Then we deposit the source and the drain metal, followed by the gate metal, known as the function layer. So to stabilize and protect the surface properties of our transistor, we put passivation layer throughout our device. Throughout our device, and then we open a specific area of the passivation like source and the drain and the gate to put our path metal to thickening the contact. At the very end, this is the end of our fabrication process, and at the end we find a device like this. When we dice our device, each dice it would come with 4x4 matrix of the sensor. So now why we choose the indium tin oxide as a gate material? Indium tin oxide is a degenerated semiconductor metal. Depending on the growth parameter and temperature of this ITO can act as a metal and semiconductor. So ITO provides a tunable electrical characteristics and is compatible to hemmed structure by forming a Schottky barrier with the semiconductor interface. And most importantly, this is a chemically and thermally stable metal. We deposit this ITO in our as a sensing layer for our device, and the input bias is 5 volt and the gate is keep floating. Now, this current output current IDS can be varied depending on two parameters like the geometry of the device and the heterostructure of the device and the gas interaction with the functional layer. So for the geometry of the device, we keep the length and the length 5 micrometer, thickness 20 nanometer, and width 200 micrometer. And this parameter will be varied depending on the interaction of the target gas. So how this hydrogen interact with this ITO layer? The sensing mechanism of hydrogen on ITO is driven by physical absorption and chemi-absorption process. The output current is changed by the absorption and disabsorption and reaction. This reaction is controlled by the temperature and partial pressure. When a hydrogen interacts with ITO, the ITO layer, the barrier height is decreased, so more electron can flow. So an increment of current is measured at the output of our device. So we build multiple test benches to characterize our sensor. This type of test bench, like where Linkam is used as a testing chamber. An automated control software is built to control the system with the help of electrovalve in LabVIEW program. We have recorded real-time temperature, pressure, and humidity information inside this test chamber. For this work, we ran two experiments. The first one, we varied the operating temperature from 50 to 300 and keep the hydrogen concentration constant 10,000 ppm to find out suitable operating temperature for our application. The second one, we varied the hydrogen concentration from 1,000 ppm to the 10,000 ppm and kept the operating temperature constant to verify the detection of hydrogen gas using ITO hemmed. In both experiments, we keep the flow rate 100 SCCM and consider no effect of humidity. So this is our fast test. So at the very, so this is the current scale of the current, and this is the scale of the time. So at the very beginning of the protocol, we kept our sensor under nitrogen for 5 hours for a suitable baseline. Then we exposed 10,000 ppm of hydrogen for 1.5 hours and given 3 hours to regenerate the sensor. After each regeneration, we changed the operating temperature like from 50 to 100 degree. When we switch from 50 to 100 degree, we wait 30 minutes to stabilize our sensor. And by this way, we vary the temperature from 50 to 300. We can see from here with the increase of temperature, the baseline of the sensor was decreasing. So this is the magnified version of the output response at different temperatures. So it's very clear that our sensor response is much depend on the operating temperature. So we can see two curves here, the sensitivity versus temperature. And at the beginning of the sensitivity, the sensitivity increased with the increase of temperature, but after a certain point, it again dropped. The other one is the response and recovery time versus temperature. With increasing temperature, the switching speed of the sensor decreased. By analyzing two curves, we choose the suitable operating temperature 200 for application. You may wonder like why we choose 200 instead of 100 where the sensitivity is very high, close to the 10%. There is a trade-off between sensitivity and response and recovery time. If we choose the highest sensitivity, the response and recovery time is so high, so the sensor is declared as a slow sensor. So for application, we had a reasonable sensitivity and response time and recovery time at 200 degree, 200 degrees. So we choose 200 degree as optimal temperature. Now we know the operating temperature of our sensor. For the second experiment, we fixed the operating temperature to 200 degree and varied the concentration from 1000 ppm to the 10,000 ppm. And at the very beginning of the test, the sensor kept under nitrogen for 5 hours for a stable baseline. Then we exposed 1000 ppm of hydrogen for 1.5 hours and given 3 hours to regenerate the sensor. This way, we increment our concentration from 1000 ppm to the 10,000 ppm. The output current increase with the expose of H2 concentration and recovered initial state when H2 was turned off. Beyond 8000, we can see the sensitivity. This is the sensitivity curve versus concentration. So we can see with the increase of concentration, the sensitivity was increasing. But beyond 8000 ppm, the sensor faced a partial saturation because of the H2 molecules may fill available absorption site, gain boundaries, and pores of the functional layer. We tested our sensor for from 50 ppm to 20,000 ppm of H2. We are able to detect throughout this range of concentration with insignificant saturation phenomena. So the ITU-based sensors performance has been analyzed with 2 experiments. First, by varying the temperature, and second one, the varying the concentration of H2. The best operating temperature was found 200 degrees from experiment 1, and the ITU-based H2 HIMT sensor is capable to detect the wide range of concentration with the high sensitivity 2.95% for 10,000 ppm of hydrogen from the second experiment. We found it. So in coming future, I have a plan to control the ITU functional layer by adjusting the growth parameter. Then I want to use this sensor for detecting different kind of gases for CO2, CH4, and test them under air and nitrogen. And at the very end, I have a plan to design a very selective sensor. Thank you, everyone. Thanks for watching.